Okay, so in this video, we'll talk about the characteristics of the normal distribution, and then toward the end, how that relates to z-scores. So there is a relationship between z-scores and the normal distribution that comes in handy a lot of times when we're analyzing data. Okay, first, take a look at these scary equations and tremble. Actually, they're just the same equation, just doing that good old math thing where different mathematicians or statisticians use different symbols just to drive home the point that symbols are arbitrary. But both equations say exactly the same thing. Exp here, exp, just says raise e to the power of whatever's next to the exp. And that's what this is. And of course, this equation here uses t to mean whatever is on this axis here, and this equation uses x for the same thing. So the x and the t in these two equations are equivalent to each other. So these are the same equation, and it is the equation of this distribution. So you would have a particular variability, specifically the standard deviation measure of variability, and a particular location on the number line, this mean right here. And given that, you input a value right here, and this equation tells you how high to draw your line at that point. So you're entering a value on this axis, and this equation just tells you how far up the line goes at that point. So that's the equation of the normal distribution. You don't really need to understand well, I guess you need to understand that that's what the equation does. But beyond that, just understand that the normal distribution is defined by an equation. Okay. Oh, and I wanted to mention that E here, E is a constant, that's Euler's number, and it has a value of about 2.71828. When you plug into this equation, well, it tells you how high the curve is. There you go. Okay. I was just reading my notes here and realized I'd already said all that stuff. All right. So the normal curve, or the normal distribution, has several useful properties for us. First, the units on the x-axis are standard deviations. So these units right here, standard deviations. That will be important in a few minutes when we talk about the z-scores. Next, the normal curve is symmetric about the mean, which means that the mean is always right in the center, and on either side, the area under the curve is exactly the same, exactly half of the total area under the curve. The area under the curve is important because, remember from the distributions and data videos, where this smooth curve comes from, you can think of the height of the curve as representing probability. Technically, it's not the height that represents probability, it's the area under the curve that is probability. But the higher the curve, the higher the area under it, and hence the higher the probability. So, if you were randomly sampling one observation from a normal distribution, the probability that you would pick an observation from the lower half, below the mean, is exactly 0.5. And likewise, the probability that you would pick an observation from the top half, or above the mean, is exactly 0.5. So it's like a coin flip. And you can look at other landmarks on the normal distribution, the normal curve, and similarly figure out what proportion of the whole distribution lives under the curve relative to those landmarks. For example, a proportion 0.3413 or 34.13%. So remember, proportion percent. To get the percent from a proportion, you just multiply the proportion by 100. But other than that, proportion and percent are really, the same information. So a proportion of 0.3413 or about 34.13% of the total area under the curve is between the mean and one standard deviation above the mean. And because the curve is symmetric about the mean, 34.13% also lies under the curve between the mean and one standard deviation below the mean, which in turn means that 68.26% of the total area under the curve lies within one standard deviation of the mean, either above or below. So when we use that term within a standard deviation of the mean, we mean both above and below the mean, but no more than one standard deviation of distance from the mean. And similarly, a proportion of 0.1359 or 13.59% lies between one standard deviation and two standard deviations above the mean. And by symmetry, the same holds for one standard deviation between one standard deviation and two standard deviations below the mean. So about 13.59% here, about 13.59% here, and a total of about, let me go to the next slide, which means 47.72% of the area under the curve is between the mean and two standard deviations above the mean. Another 47.72% is between the mean and two standard deviations below the mean. And 95.44% lies within two standard deviations of the mean, above or below, which in turn means only 4.56% of the area under the curve is further out than two standard deviations, because the total has to add up to a proportion of 1, or a percentage of 100%. And each of these proportions is a probability, the probability of getting a value in that range if you randomly sample from a normal distribution. Now, we can go on like this pretty much forever, but we don't have to, because it turns out you can find out the probability for any range you want. How do you do that? Remember what that x-axis is. Those numbers are numbers of standard deviations. And remember z-scores? What were the units of z-scores? Units of standard deviation. So, if you have data that you can consider to be normally distributed or pretty close to normally distributed, you can find out several things. You can find out the probability of getting a z-score as extreme or more extreme than the one you got, and the probability of getting a z-score between the mean and the one that you got, or the probability of getting one that is within the number of z-scores above or below the mean compared to the one you got. How do you do that? Well, in the real world, software is going to do it for you. But in learning statistics world, you can find a z-table, also known as the normal distribution table, and look up a z-score. Once you have the z-score, most z-tables will tell you two values, the proportion bigger than that z-score and the proportion between the mean and that z-score. Let's just do one easy, quick example. So here we have just a portion of a z-table. You can see the, here, let me switch to the laser pointer here. There we go. Here you see the column with z-scores in it, area between the mean and the z. That would be this area right here, whatever your z-score is, between the mean and that. And then the area beyond z. So suppose I calculate a z-score and it turns out to be 1.37. That's about where the arrow is pointing, right here. Right there. On the normal curve. You can see from the little bit of table that the area under the curve between the mean and 1.37 is 0.4147, right here, or about 41.5% of the total curve. The area to the right of the arrow, so this area right here, under the curve in this area, that area is given right here, 0.0853. or about 8.5%. So knowing these two things, you could figure out other things, like how much of the curve is less than 1.317. So in other words, if you wanted to know what proportion of all the scores are lower than the score that we calculated, 1.317, you can take the area between the mean and this score and add to it the total area under the curve that's below the mean, right? So we've got this 0.4147, that's the area from the mean here up to that z-score, so that total area right there. Add to it the area that's below the mean, and what was that area? Well, that area is exactly 0.5, right? Because half of the observations are below the mean. So we add 0.5 to the 0.4147, and we can figure out that the total area, it would be, what would that be? 0.9147, or about 91.5% of all the scores lie below a z-score of 1.37. So you can use this relationship between z-scores and the normal distribution only when your data are normally distributed to begin with, or at least close to normally distributed. By doing this, we can set limits on what we want to call big or small or outside the norm using percentages, and then go from the percent we want to the z-score cutoff that we would have to use to get that percentage. For example, suppose I want to say that anyone in the top 5% of sales in a given month gets a bonus. I can look up the z-score that has 5% of the observations above it. Turns out that's around 1.65. Then I could calculate everyone's z-score and give bonuses only to those with z-scores bigger than 1.65. All right, that's enough for now. Now you hopefully understand a little bit better the relationship between z-scores and the normal distribution, and you are now ready for that crowning glory of statistics, the linear correlation. Next video.